this video, we'll be looking at the first half of the P5 Forces in Motion topic, specifically the Forces section. Now we're going to branch this into five subsections. First of which, we'll be looking at the basic idea of quantities. So this represents anything you are measuring. And this is where we split it immediately into the two key definitions you need to know about regarding quantities, which is scalar and vector. Now you must be able to compare these two, give a definition, and provide examples. So a scalar value has only got a magnitude. Now that means it is just a number without a plus or a minus, just a value. So remember, the word magnitude means size. So something you measure as just a number. So the key examples for this that you need to know are things like speed. We have distance. And then slightly more obscure ones such as time and temperature. Now, when we look at vectors, it's again a comparison. So we need to use the term magnitude again because it does have that. It does have a value. But the difference is it has a plus or a minus value. So it has magnitude and direction. Now that also means we have a visual means of illustrating this, which is through use of an arrow, which is the most common way to illustrate vectors. So for basic examples for these, let's match up first. So velocity is one of the key examples you need to know. And it comes up much later in the topic as well, in the second half of P5, as does displacement. Now I've started with these two because they match the first two examples for scalar. So where we say speed, that's just a number. The velocity is that number in a specific direction. So it's a directional version. Same as distance and displacement. Distance is just how far, displacement is how far in a straight line. Now we also have acceleration, which is formed from using velocity as a calculation, as is momentum. So these are further examples that come up in the second half of P5. Now, a key example I haven't written here is forces, because we'll obviously see that very shortly, but they are obviously represented by arrows as well. Now, just remember, direction means positive or negative. So all of these can have positive and negative values. No scalar value has a positive or negative, apart from the trap of temperature, because temperature scientifically should be in Kelvin, which starts at 0. But because we use degrees Celsius, that has a negative because we're measuring from another arbitrary value, which is technically 273 degrees Kelvin. So it's a bit of a trick. Don't fall for it. Next, we are going to look at the forces themselves. Now, I'm not going to list all the different names associated with forces here, but I would recommend that after you've produced this mind map, you spend some time listing and identifying as many force names as you can, especially if you can add them to a diagram. But we're going to split this into the basics. We're then also going to look at the slightly more advanced parts, so things relating to determining resultant force. And finally, we're going to look at the 3 Newton laws. So, in terms of the basics, we know that forces are all vectors. Every single one of them. Doesn't matter what the name is, it's a force, and therefore a vector. And as a result, we will draw them with arrows. Now, arrows give us a wonderful tool to describe the force. Mainly directional. So we know a vector has to have a direction. So an arrow shows the direction that the force is acting in. The length of the arrow actually also represents its magnitude. This isn't always very clearly illustrated. Sometimes you'll just have a number instead. But if you're comparing forces with or without numbers, they should be scaled. Now, when we look at resultant forces, what we're really starting with is a free body diagram. So a dot, an emphasized dot, as our object, and a series of forces acting on it. So I've labeled this with 4 forces. So we've got 4 newtons up and down, 5 newtons to the right, and 2 newtons to the left. Now to find a resultant from this, we have to take the vertical forces separately from the horizontal ones. So vertically, we can see 4 up and 4 down cancel out. Horizontally, 5 minus 2 leads to 3 newtons to the right. So all we have is one force at the end. So the basic rules for doing this is just the fact that if you have multiple forces pushing in the same direction, you add them up. If they're in opposite directions, as we saw with these in this example, you take away. The only extra part is that if we end up with one vertical force and one horizontal force when we've done the cancelling out as we've done in this example, then you need to find a single force arrow in between the two. Now, as that would not be in this 90-degree separation, it requires some trigonometry. So to determine the magnitude of that arrow, you can use Pythagoras, because you'll have the 2 shorter sides of the triangle to find the hypotenuse. But to find the angle at which it's positioned, you would then have to use the classic SOHCAHTOA. So those would be the higher end questions requiring that. Now, as far as Newton's laws go, you need to be able to define the 3 laws and identify them in different case examples. Luckily, they can be simplified quite easily. The first law is to do with resultant forces being equal to 0. So if you have no resultant force, so every force is cancelled out, then you will have no change to the motion. So no change in speed. So an object that's stationary stays stationary. Anything that's moving at a speed continues at that constant speed. Now for the second law, it's the opposite of that. If we have a resultant force that is not 0, so any number, positive or negative, then what you end up with is a change in the speed, which we can define as an acceleration. Now don't worry about acceleration or deceleration. It's the same thing. It's just positive or negative directions. So changing speed or the word acceleration are perfectly fine. So an acceleration occurs. Now this is tied to the equation F equals m times a. So force is equal to the mass times the acceleration. It's worth remembering that this one can be linked to gravity as well, where weight would be the force and the acceleration is the acceleration due to gravity, 10. Now, the final law is the easiest to remember, but can be difficult to phrase as well. Now, it doesn't relate to resultant forces directly. Instead, it's the idea that if you have two objects in contact, if one of them applies a force on the other, it will apply a force back of equal size, but opposite direction. So the magnitude of the reaction force that's present will be equal to the force that was applied to it, but acting against the original force. So an example here, if we have a wall and you push against it with a force, that wall will push back with the same amount of force. To give an even simpler example, you could consider standing on the ground, for example. So if you stood on the ground, your weight is pulling you down, and the ground itself pushes up with a reaction force. Now for the next strand, we are going to start looking at things that cause rotation or rotational motion. Now this is split into two sections really, the first being center of mass. Now center of mass defines what happens here, whereas moments are the rotational motions themselves. So when we regard the center of mass, what we first have to think of is a shape. Now the center of mass is the point through which the weight of that object will pass through, so the arrow representing the weight. And with normal symmetrical shapes, it's very easy to identify the central point as the center of mass. But remember, if you're trying to find it for an irregular shape, you're normally going to do an experiment suspending the shape from different corners or different points and hanging a plumb line to find the line of the weight. But the main relevance for this is if we have an object with weight acting from its center of mass and you try to topple it, as long as the weight passes through the corner or is on a lower angle than the corner, it will remain balanced, or it'll topple back to how it was. If the line of the weight passes the corner, it will fall over. Simple as that. So just think of the position of the center of mass, draw the line of the weight, see. Now for moments, again, diagrams matter hugely. So we start off with a basic seesaw, and every situation can turn into this. Your pivot will be at a set point, usually either in the center or on one of the edges. We also have two objects in this one, so I'm going to say the first one's applying a force or weight of F1 and the second object F2. Now when we measure distances, they may give you the whole distance of the seesaw, but we care about the distance from the pivot to the object with the weight. So we've got two distances here, and let's label them D1 and D2 to match these forces. So every time you measure distance, it is the perpendicular distance to the force, as you can see 90 degrees here, and it is from the object with the force to the pivot itself. Now, when we look at the equation for this, we find that a moment, the turning force, is equal to the force that's being applied times its distance from the pivot. most important thing is the law of conservation, and that says that a clockwise moment, all of the clockwise moments in the system equal the anti-clockwise moments, again, all the things causing it to turn anti-clockwise, if the whole system is in equilibrium. Now, by equilibrium, we mean balanced. So they usually show you a diagram that's balanced, but it might not be. They might ask you to find out if it's balanced, in which case both moments should equal each other, or they'll tell you it is balanced and ask you to find one of the forces or one of the distances. But anything turning it clockwise will cause it to rotate this way, and anti-clockwise this way. And I always like to label it just to make it clear, and that then lets me piece them together. So in this case, if we know it's balanced, then we know that everything causing it to rotate clockwise is going to equal the anti-clockwise. So our anti-clockwise side is F1 times D1, and our clockwise moment is F2 times by D2. These are only equal if they are balanced, which we use the term equilibrium for. And it's worth saying the word equilibrium is often worth a mark on its own when relating to this topic. So, for the next branch, we are going to look at pressure, and this is a triple only section. So this bit's almost more likely to come up simply because it's specifically targeted at your paper. So we can split this into the two parts, basic and column. Now for the basic, we'll start off with the equation. Pressure equals force over area. So force applied to a cross-sectional area. And this can count as solid, liquid, gas, whatever, doesn't matter. But what we care about most is liquids, because we know that we can manipulate the shape of a liquid, but as long as it's held under pressure, the pressure is constant, which is used in hydraulics. Now, hydraulics are a system abusing this knowledge. Now, if you consider a syringe, so it's a sealed syringe here, with a fluid, and that's at a pressure. Now, when you apply a force to the plunger, the cross-sectional area will compress the liquid as much as possible. As it compresses it to its maximum compression, you will reach a fixed pressure. But if this was contained in a closed system like this with two plungers, the pressure throughout the fluid inside will be constant. So when we end up with a force pushing out on the second plunger, you can notice immediately that the area, the cross-sectional area of that plunger, is bigger. So how will that affect the force? Well, if we rearrange the equation, we can see that the force is equal to pressure times area. So consider that in terms of proportionality. If pressure is constant, that tells us that force is proportional to the cross-sectional area. So if that's the case, the area is bigger, so the force will be bigger. And this is how we can multiply the force applied in a system. So if you press your foot down on a brake, the brakes applied to your tires, to the wheels, will be far greater than what your actual leg muscles are applying. So it's a clever way of increasing or decreasing force based on one single action, causing an action elsewhere. Now for the column part, we're given this equation, and it's an odd one. and this is the main reason this is only in triple. We end up with pressure equals rho hg, and these are defined on the equation sheet. Rho we know is density, but you need to remember that density is mass over volume, because you may be required to do that calculation first before attempting a question using the above equation. So it's tying together a couple of topics there. H is a tricky one. It's both depth and height. So as we're dealing with a column of fluid, this could represent the volume of air above you, the volume of water above you underwater. Okay, it could be just a column of water and how much pressure is at the bottom. And usually it is the bottom, in which case the height of the column is the same as its maximum depth. So height of the column is usually what it actually represents, but really it's how deep you are in the fluid. And G is gravity, which we know, or should know, is 10 newtons per kilogram on Earth. And that applies throughout the entirety of this topic as well. So it may be worth adding to the forces part earlier. But that's it. This equation is just a case of application, rearranging, and understanding of context. Now the final bit we're going to look at in this video is Hooke's law. Now luckily this is quite straightforward. We know the equation is F equals K times E. E representing the extension of the spring, and K being the spring constant. Now this is a value that is unique for the material you're using, so unique to that spring or that elastic material. So it can be used to identify what it is, but it's usually something that you're going to have to work out. There is a second equation tied to this, and also tied to the first topic, P1 energy. And that is one that's given in the equation sheet, E equals 0.5 or half times K times E squared, again representing extension and spring constant. Now this means the energy stored in a spring. So it's a given equation, and it's given so that you know what K and E represent. It also allows us to tie to the normal spring constant equation and form a graph with some meaning. So following the experiment of stretching the spring by adding masses, you would end up with the force or weight as your independent variable on the y-axis here, and our dependent variable extension on the x-axis. And this gives us a straight line. Now this is representing the fixed value for k. So if you measure the gradient, change in y over change in x, your gradient will equal k. So it's a way of proving the identity of the material you're using, or to help identify it maybe from a table of data. However, if you instead measure the area under this line, that will give you your value for energy. Okay, so it represents the energy stored in the material, or work done in stretching it. So quite a useful graph and nicely tied to practical work as well. And there we have it. P5a, the first half of P5 covered. Thank you for your time.